All right, the first set of notes, we are going to be introducing some types of mixtures, some examples of solutions, what is solubility, and then specifically how to write complete and net ionic equations. So just broadly between homogeneous or homogeneous and heterogeneous mixtures, homogeneous is uniform distribution of particles, whereas heterogeneous is non-uniform. So, for example, if we look at a heterogeneous mixture, it's uneven distribution throughout the particles. Uh, Suspensions are a type of heterogeneous mixture. And so, like oil and water, for example, you can mix it up and shake it, and it will eventually settle out. So that's definitely a suspension because we can separate it and we can see the difference between the two layers. Muddy water is the same way. You can filter it and remove that mud. You can pick it out physically. So a suspension is anything where we have very large particles where we can see the difference between that and another part of the mixture. We also have what are called colloids. Okay, colloids are in between a suspension and a solution. Solution, by the way, is homogeneous. So heterogeneous would be considered suspensions. Colloids will appear homogeneous, but their particles are actually a little bit larger than a solutions. An example is paint, milk, cheese, fog, mayonnaise. Those are all gelatin. Those are all types of colloids. And one way to determine if it's a colloid versus a suspension or a solution is to shine a light through it, and it's going to exhibit what's called the Tyndall effect. So the Tyndall effect, the light gets scattered. If you think of something we're all familiar with on a dark night that might be foggy, and your headlights kind of scatter and create this pattern of light, that is definitely a colloid. So I have a quick video just to show the difference between the three. Okay, the third type of mixture is homogeneous, where you have even distribution throughout, and this is a solution. So solutions are homogeneous mixtures of two or more substances uniformly dispersed throughout. For example, lemonade, those are small enough particles to be dissolved in that water, so you're not going to see pieces of the lemonade normally. Because it has the same composition throughout, a solution has the same properties throughout. We have two parts of our solution. We have what's called the solute and then the solvent. The solvent does the dissolving, the solute is what's being dissolved. So if you're talking about something that's an aqueous solution, water is going to be your solvent, and then whatever you're dissolving, say you're doing salt water, salt would be the solute. Now, you don't always have to have something that's water-based. Or often think of solutions as water-based, but it could be like an alloy. An alloy is a mixture of metals. So whatever the one that's in the greater quantity is going to be the solvent, and then the lesser quantity or quantities, if you have several metals, is going to be the solute. So those are the definitions. Some other examples of solutions, like I said, you don't have to have just water, but you can have gases dissolved. Like, so for example, if you dissolved oxygen in nitrogen, Nitrogen would be your solvent. Oxygen would be your solute. You can dissolve gas in liquid. So, for example, any carbonated drink, carbon dioxide in water. Liquid in liquid, alcohol in water would be an example. And then we have some definitions or vocabulary words. Immiscible means that things are not able to be soluble in each other, and they thus form separate layers. So I think of immiscible like mix, so immixable kind of. You can't mix it. So think about your oil and water. Miscible are things that dissolve freely in one another. So, for example, like two polar liquids like alcohol and water, those would definitely be miscible. We could also have solid and liquid. That's something we think of often, like if we dissolve sugar in water. Or we can have solid and solid, such as I talked about the alloy example. When you make brass, for example, you dissolve zinc and copper. So here's an overview of just the difference between solutions, colloids, and suspensions. Solutions are homogeneous. Colloids we'll consider heterogeneous, even though they look homogeneous. And then suspensions definitely heterogeneous. Particle size, small, medium, and large. Particles settle out. They do not in solutions or colloids, but they do in suspensions. And then as far as if we're able to separate by filtration, we cannot do that with solutions or colloids, but definitely suspensions. And finally, the Tyndall effect is just going to affect colloids and I guess sometimes suspensions. Solubility is a measure of how well one substance dissolves in another. This is our last topic. So the amount of substance required to form a saturated solution with a specific amount of solvent at a specific temperature is the little bit more extended definition. Like often dissolves like is useful for predicting solubility. That means polar dissolves polar and nonpolar dissolves nonpolar. Soluble is capable of being dissolved. All right, general solubility guidelines. This is something that you are given in your notes here, but also it should be on your Unit 9 reference sheet as far as which ions are soluble. So we're talking about aqueous solutions here, and we've seen these types of reactions many times. You take two solutions and something precipitates out. That means that it's insoluble. So what we're doing is we're going to predict the solubility of two ionic solutions mixed together, and we're going to predict if there's a precipitate, and then we're going to learn how to write these equations. So this is just a reference. We will use this as we do some practice. Water, before we do the practice, we'll talk about water for a second, is a universal solvent. That means a lot of things dissolve in it because it's very, very polar. It's a liquid at room temperature, just some properties of water. It has high melting and boiling points, and this is due to the strength of its hydrogen bonds from last unit. It does have high specific heat. It means it takes a really long time to heat up, but it takes a really long time to cool down. If you think about like the lake, in the summer, it gets warm, and then the air stays pretty warm because we have a large body of water that stays warm for longer. So it has to absorb a lot of energy in the form of heat to increase its temperature. That's why it takes some time. Dissolving, the definition of dissolution is the process of dissolving and forming a solution. The solute separates into ions or molecules, and each one is surrounded by molecules of solvent. So basically, the water surrounds like a salt crystal, and it's going to tear apart those ions. And that's what dissociation means. It means separation of ions that occur when an ionic compound dissolves. Solvation is that process between the solute and solvent particles when the solute particle is surrounded by molecules of a solvent. All right, our last thing that we're going to look at is writing net ionic equations. It's a process. We actually have to write our molecular equation, then we're going to write a complete ionic equation, and then we're going to write the net. So the net ionic equation, if you think of like your net pay, if you have a job, it's after everything is taken out. So this is often written for reactions of ions in aqueous solutions instead of a chemical formula equation. This is kind of like your take home, like what is really happening with these ions to create a precipitate. So it shows only the compounds that undergo a chemical change in the reaction. There's other ions called spectator ions that remain unchanged on both sides of the equation, so they get canceled out. So let's consider the double replacement reaction between zinc nitrate and ammonium sulfide. What we're going to do, and on your practice 1, there's an example for you so you know the format. I will do a couple examples at the end of the slideshow if you want to watch that for additional examples. But we're going to write just a regular old chemical equation with formulas and states of matter. The states of matter on the reactant side is always AQ, aqueous, because they're both in solution. We will use our solubility guidelines chart to help us determine if they're aqueous or solid, and we'll balance it. Then we're going to rewrite the overall ionic equation, or complete, overall or complete, same thing, by separating the ions. And then we're going to cancel out any spectator ions and rewrite the net ionic equation. So for example, zinc nitrate and ammonium sulfide. Okay, first of all, you have to come up with the formulas. That's crisscrossing if it's not provided to you. So you're going to write the two reactants, and then we're going to predict the products. All right, before I show you the two products, you can just remember do a outers come together, zinc sulfide and ammonium nitrate will come together. So we're going to rewrite that. However, we're going to have to figure out, is it solid or aqueous? Now, most of the time, just for practice sake, one of these is going to be solid and the other is going to be aqueous, but it's totally expected for it to also, it could be both aqueous. That means there's no reaction. So AQ means it remains dissolved, and solid means if there's a reaction and it precipitates out. So our two products, again, is zinc sulfide. If you do your outers together, this is double replacement, and then ammonium nitrate. Now, if I go to my, this is your Unit 9 reference. So if you don't have that, I would just pause a video and grab that. You can use this solubility guidelines to figure this out. So again, remember zinc sulfide is one of our products. And so here's sulfide. The way this is set up is that these are anions on the left here. So sulfide is right here. And it says soluble only when combined with group 1 ions, which zinc is not a group 1 ion and is not falling into any of these exceptions. So that means it's not soluble. If it's not soluble, then we're going to write solid, or you can write that downward arrow for precipitate. So that's our solid. And remember that our other product is going to be ammonium nitrate. Now, all nitrates are actually soluble. So if you look at all of this here, any of these ions, doesn't matter what cation is with it, it is soluble. So notice zinc sulfide has a solid next to it, and then we have ammonium nitrate that remains AQ, aqueous. Our next step is to balance it. So we just needed a 2 right there. Our next step now, this is like the most tedious part, is to break apart or the dissociation. That means they're broken apart in solution. We're going to write all our ions. Now notice that AQ is always both of them for this side. So we're going to break up all these ions. And then we're not going to break this one up because it actually reacted. And then we're going to break this one up because it remained soluble. So this is like very detailed because you are going to have to write, we have 2 types of ions for each compound, and you're going to have to write the charge, and you also write AQ. So it's going to be zinc plus, and then we have 2 of these, 2 nitrates at a 1- charge, AQ. Then we're going to break up this one, there's 2 ammoniums, okay, AQ, plus a sulfide, AQ. So notice, this is broken up, this is dissociated, this is also dissociated. When I say dissociate, I mean break up. These two are, okay, so we have 4 ions on the left side, all AQ. So there's all of these state symbols, there's charges every time, and then if we have more than one, because we balanced it, we need to write that as well. Now, on the right side, we are not going to break up zinc sulfide because it actually reacted. We're only going to break up things that are AQ. Then we're going to break up these on this side. So it's going to be kind of repetitive. But what this means is that it remains soluble. So 2 ammoniums and 2 nitrates. Now, this is called my complete or overall ionic equation because we showed everything. The point of this is to show what's happening in solution. What we're going to do now is cross out our spectator ions or underline them. I usually just underline mine. And those are the ones that remain. The spectators mean they're not participating. So they remain soluble on both sides. So whatever didn't create zinc sulfide. So we have ammonium and nitrate. Notice ammonium and nitrate look the same on both sides. So these are crossed out or underlined, however you want to do it. And then finally, our net. Remember, our net is like take home. Like this is what we take home after everything is said and done. It's just going to be zinc and sulfide reacting together to create zinc sulfide. So that's actually the net right there. All right, you can pause or stop this video if you want and try the practice 911, or if you'd like some more practice, you can continue watching. I have 2 more examples. You'll have to have your solubility table handy still. Okay, so I just have 2 random examples here. I am going to, oops. Okay, so let's see, we have silver nitrate. Remember, our first step is to write our full balanced equation. And calcium chloride. Okay, and so what we're going to do now is we're going to do a little crisscross. So silver chloride and calcium nitrate are going to be our 2 products. Now, we have to figure out, are these soluble? So I'm going to go back to my so what was that again? Silver chloride and calcium nitrate. So if you remember, no, all the nitrates are soluble. So that's going to remain AQ. And the other one was silver, just forgot what I was doing. Silver chloride, I think. Yes, silver chloride. So silver chloride is not soluble. So this is chloride. It says everything is soluble except when combined with silver, copper, or lead, so silver falls in that exception category. So let's see, we'll go to here, solid. This is AQ. Now, our next step is to break up everything. So silver has a 1+ charge, and you can look this up if you need to. There's only one of them. That's the charge, AQ. There's 1 nitrate that has a 1- charge, AQ, plus calcium has a 2+ charge, plus there's 2 chlorides. Oh, I forgot to balance. Let me go back and do that. Do we need a balance? We do. I'm going to put a 2 here and a 2 here. My bad. I'm going to fix that. So there should be 2 of these and 2 of these. All right. Keep going here. Now this is solid, so we do not want to break it up. But we do want to break up the calcium and the nitrate because they remained aqueous. All right. Now, what we're going to do is I'm going to underline, which you can cross out if you want, the spectators. Spectators are ones that remain soluble. So, what remains unchanged on both sides? We got nitrates, and then we have calcium. So, those are my spectators. And what I'm going to do when I write my net is I'm going to drop it. So, I'm going to use this color again. So here's my net. Just rewrite what I did not underline. This is really what's just occurring. Okay, that's number one. Number two, I'm gonna go ahead and write that. Again, this is old stuff like figuring out formulas, crisscrossing. All right. Sodium and hydroxide are going to get together, strontium and phosphate. So let's go to strontium phosphate and sodium hydroxide. Let's go to my table. So sodium hydroxide, here's hydroxide, soluble and combined with group 1 ions. Sodium falls in that category. So that is soluble. And then the other one was, again, strontium phosphate. So strontium phosphate, here's phosphate here. It says soluble only when combined with group 1 ions or ammonium. So strontium phosphate is my solid. And it doesn't matter what order I write this in. That is my solid. Oops, that should be a 2. Okay, and then sodium hydroxide remains AQ. Okay, we need a balance for sure. We have 3 here. We only have 1 here, but then I'm looking at the hydroxide. There's 2. So we're going to need to do a least common multiple, 6. So 2. It's going to give you 2 phosphates. 3. You're going to need a 3 here. 3, 3, 6. Okay, now we're good. All right, now we're going to break it up. So we're going to do our overall. All right, so this one's a little more writing because just, oops, we do not have 2, we have 6. Let's erase that. Okay, we have 6 because I have to don't forget to multiply. So there's 6 sodiums, and there's 2 phosphates, and then there's 3 strontiums, and there's 6 hydroxides. Okay, so I break up the entire left side. Then we are going to leave this alone. We are going to not break that up. And then we're going to break this up because it remained aqueous. Then we are going to underline our spectators. So whatever didn't create this. So hydroxide and sodium. Those are my spectators. Now let's go ahead and drop our spectators to write our net. So our net is 2 phosphates and 3 strontiums. Gives me strontium phosphate. And that is it. So try the practice or get some extra help if you need to. But this is a little bit of combination of or accumulation of skills that we've done throughout the year. So if you forget and you need a little refresher, ask for help.